Hi all, welcome to my YouTube channel Know About Embedded System. In today's video, we're going to continue with the ADC. In the previous video, we have discussed about what is ADC and how ADC works. But in today's video, we're going to discuss how to develop embedded C code for your ADC and how we can program ADC and how we can convert analog to digital. So let us start the video. Before starting the video, if you're a new viewer to my channel, kindly subscribe my channel and gain the knowledge on embedded system. So let us start the video here. So how to develop embedded C code for your ADC. So already theory part we have discussed in the previous video. You can just watch that video. And today we will discuss only about developing the code for your ADC. Before going to the code, currently what we're using in our development, the first important thing is we're going to use LPC1768 microcontroller. I hope everyone knows that already. We're going to use LPC1768 microcontroller, which is a 32-bit of microcontroller. In this LPC1768 microcontroller, we have 12-bit ADC. In this, so this is the one important thing we should know here. So we have 12-bit ADC. So what do you mean by 12-bit? That means it will produce 12-bit resolution. Okay. So and also we have 8-channel ADC. ADC we have 12-bit ADC and we have 8-channel ADC. So what do you mean by 8-channel? 8-channel means we can interface up to 8 different channel, 8 different analog inputs we can interface. So currently what you're seeing on the screen here, this part, so this is what the channels are nothing but analog input channels, and they have given some namings like analog input 0 1 2 3 up to 7. We have option here, and also the pin numbers you can see here, so which are connected to port 0.23 0.24 0.25 and P0.26. Okay, so we have LPC1768 microcontroller and we have 12-bit ADC inside. This ADC is of 12-bit, and then we have 8 different analog inputs, and the numberings I have mentioned here. Okay, this is a one part. Second part, after doing the coding, you can display output in the LCD, but I'm not able to show you on the LCD because of some other issue, but I will show you output in the local variable. So I will show you output in the simulation, debug simulation, and I will show you in a one global variable. So whatever data we are converting analog to digital, that data I will show you in a one of the global variable. Okay, so this is what how it looks like when you want to develop a code. So we have to consider analog input channel, how many channels you want you can connect, but in this microcontroller we have 8 different channels, but even in industry we will have up to 64 128 channel ADC also we will get. Up to 128 channels we will get in the industry. For demonstration purpose, I have considered 0.25. So I'm going to show you output on a P 0.25, which is I'm assuming the temperature sensor is connected to P 0.25. That is nothing but analog input to 2. So we have to develop a code for analog input to 2, which is connected to 0.25. Okay, so this is a brief introduction before starting the code. Now, before starting second part of the coding, I just wanted to show you our ADC chapter. I'll just go to the ADC chapter and then we will understand some of the registers here. Here you can see this is chapter number 29. So this is, you know that already. If you're following my channel, definitely you will be knowing what is this document. So this document is nothing but LPC1768 user manual. In this user manual, they have explained all the components, all the peripherals which are available in the microcontroller. So currently I'm discussing about ADC here. This is chapter number 29. You can just click on the chapter number 29 and it will directly take you to the ADC. So here you can see the chapter number 29 and ADC it is. Okay. So whatever I have explained, same thing here also they have explained in a brief. I told you in our LPC1768 microcontroller we have 12-bit. So we have 12-bit. So we have 12-bit ADC and up to, yeah, the operating frequency of this ADC is 200 kilohertz. Okay, so 200 kilohertz and 8 analog inputs. This is what I have shown you already. We have 8 analog inputs, right? So this is a simple information. but our scope, yeah, here you can see these are all the input numbers they have given, AD0 to AD0.7. So that is not our scope. Yeah, our scope is to understand the different registers. So with this document, I wanted to explain you two important registers. One is called ADCR and one is called ADDR. Okay, so ADCR is a one important register where we're going to configure our ADC, and then we have ADDR, that stands for data register, where you will get our result, or you can say it's data. So these two registers we have to understand, and using these two we have to develop the code. Let us see register explanation, then we will go to the coding part. Okay, here you can see this is what I told you. This is a one important register we have to understand, and there are some series of registers available from ADDR0 to ADDR7. There are totally 8 channels are there. For each channel there is a dedicated data register. That is what they're showing here. ADDR0. ADDR means analog data. ADC data register. ADCR stands for ADC control register. Okay, so let us explore, and later we'll go back to the coding and we'll develop the code. Yeah, so this is ADCR. ADCR, that stands for ADC control register. In this there are different fields they have defined. If you see one by one here, they have defined something called a selection, then they have defined something called as clock division, then they have defined. So all these things we have to understand, then we have to do the coding. Let us start with the first one, the SEL. So what do you mean by SEL? So if you read the statement here, you will understand SEL stands for channel selection. SEL stands for channel selection. So what do you mean by this? So this SEL field will define which channel you can select, which channel you are going to select. So there are 8 bits they have defined, each bit for one channel. I have already told we have 8 different channels. For each channel there is a 1 bit is defined in this field, that is called as selection. SEL stands for channel selection. You can select any channel. That's the first point you should know. The second point in this register is clock division. CLK this is nothing but clock division. So this clock division is used to step down your peripheral clock. Okay, so if you have higher clock, that higher clock will be stepped down by this division. There is a simple formula, peripheral clock divided by clock division. So we have to divide by some value. So when you divide it, the peripheral clock will get lower. It will be divided by some x value, and your peripheral clock, your ADC clock also will get reduced. Okay, then so we have burst mode. Here you can see this is a bit number 6. Bit number 6 stands for burst mode. So what do you mean by burst mode? Burst mode means continuous conversion. What is a burst mode? Burst mode means continuous conversion. That means in an infinite loop, continuously you can convert. If you keep it in a while of 1, your ADC will continuously, without any condition, ADC will continuously convert your analog data to digital data. That is called as uh, burst mode. If you want, you can read the explanation they have provided here. The burst mode means continuous conversion of analog data is called as burst mode. And then we have something called a software control mode. Here you can see this point, you can see software control mode means through the coding we can control the conversion. So we have to develop some more part of the code to convert analog data to digital data. For that part, we will use the software conversion mode. Okay, so this is called as burst mode. And finally, we have PDN bit number 21. So bit number 21 talks about power down mode. What do you mean by PDN? PDN stands for power down mode. So whenever your ADC is not working, automatically the power will be down. Okay, so that is called as power down mode. Okay, so now, so this is our ADC register. One is a channel selection, clock division, burst mode, and then PDN mode. So all these things we have to configure in the coding part. Okay. So now let us move to the one more register called as ADDR. So here you can see ADDR stands for ADC data register. This ADC data register is having two parts. One is a result and then one is a done bit. If you watch my previous video, you will understand what is result and what is done bit. So what is a result? Result means it is a 12-bit digital value after conversion. 12-bit digital value after conversion. So result means after converting analog to digital, the 12-bit digital value will be stored in this field. Okay, that is called a digital. And positions you can see here, bit number 4 to bit number 15. Totally 12 bits they have defined for a result storage. Okay, and finally this done bit. So what is done bit? Done bit stands for end of conversion. After ADC converting analog to digital data, so your ADC will generate, or your SCR ADC will generate one control signal that is called as run bit, or you can also say it's end of conversion, indicating that conversion is completed. Okay, so these two are very important registers. One is ADCR and one is ADDR. Okay, so with the help of this we have to develop the coding. And last one more point I just want to add on here with respect to our ADC configuration. So that is your pin configuration. If you look into my slide here, I'm assuming, or let us assume, one sensor is connected to the analog input 2. This analog input 2, let us assume, or let us understand, there is a sensor which is connected to analog input 2, and that port pin is P0.25. So what is our intention here is we have to configure pin configuration as well, or pin function selection as well. That also we have to do it. Okay, so in order to do that, so we have to go back to our pin configuration register or pin configuration chapter. You can see here, this is your pin connect block. So you can come here and then slowly you can scroll down a little bit. P0.25, I have to go to P0.25. Here you can see, so this is a P0.16 and here we are. So this point we have to address. I have to configure P0.25 as AD0.2, meaning is analog to digital channel number 2, which is connected to P0.25, and the function what we have to configure is 01 function, and pin cell is 1. So pin cell 1 we have to do, and bit positions here you can see. The bit positions are 18 and 19. Pin cell 1, 18, 19 bit positions, and function is 01. Okay, so this is a one additional setup we have to do in the configuration part. Okay, so with this I'll just complete my theory part. Let us go back to the coding here and let us write the coding here. Okay, so this is, I have already written some skeleton body of the code. We will write only the main part of the code and we will check the output here. So this is a code, and this already you might be knowing. If you're a new viewer, please visit my previous videos, pin function selection. In that I have explained already what are the function of this pin function selection. So each port pin will have 4 functions that only I have created here macros. So function 0, function 1, function 2, and function 3 I have defined with 0, 1, 2, 3. So these macros are used to select the pin functions. And second point here you can see the beauty of ADC lies here, and every configuration part I have created a macro here. In the theory part just now I have discussed about clock division. There was one parameter called as clock division. So here you can see clock division I have defined with a macro 23. Then I have created a macro for PDN on, power down mode on 1, burst mode on 1, and then channel selection, channel number 0, 1. Here you can see. So how I have written the binary representation I have mentioned here. for each configuration. So for channel 0 selection, I had to pass on 0 1, then channel number 1 it is 0 2, for channel number 2 it is 0 4, and it goes on like that. And finally for done bit it is 1 left shift of 31. Okay, so these are all the macros I have already created and kept it, and I'm going to write two functions. One is the ADC configuration and one is ADC conversion. Two functions I'm going to write. Okay, so let us write first ADC configuration, and then later we will come back to ADC conversion. Okay, yeah, so here you can see this is my ADC configuration function. Already I have kept it one function, one parameter I have already configured, that is nothing but enable the power for ADC. So in some microcontrollers there will be a low power mode as well. So sometimes we have to activate some power bits. So that is what I'm doing in line number 47. Line number 47 talks about enabling the power to the ADC. So that we have to understand by reading the datasheet. So this is the first point I have to do. And second point, what I'm going to do is configure P0.25 as analog input 2. So config P0.25 as analog input 2. I have to do that. So how can I do? You know that already. So we have to use LPC underscore. So there is a pin con block. Pin con stands for pin control block. And then so we have to select pin cell 1. So just you watch the video once again, you will understand what is the meaning of all this. And then I have to select pin function 1. So this I have to go pin function 1, and then position is 18. So when I do pin function 1, left shift of 18 when I do, that will get configured with your analog input 2, P0.25. Okay, this is my second configuration of your ADC. Third configuration of ADC, I have already written the comment here. Please follow the same channel selection. The first one is channel selection. Which channel I have to select? I have to select channel number AIN2, analog input 2. So for that, here you can see channel number 2 I have to. So just make it channel number 2. Channel number 2, perform OR operation, clock division. Okay, so this clock division is defined between bit number 6 to bit number 8 to bit number 16, and for clock division also I have defined already some value, that is 23. You just copy that value and then put it here, and position you need to mention here. So what is the position? Position is 80 to 16. Just you define with the starting position, and then I need to enable the burst mode. So for burst mode also I have created a macro here. So created a macro, and then just to enable the position here, that is 16, and perform OR operation. And finally I have enabled PDN bit as well. So PDN on, so that also you can use it here. PDN bit is 21. Okay, so this much is required for configuration, and then I need to define register here. So if you want to define the register, I have to go to the ADC underscore LPC underscore LPC underscore ADC. So this is how we're going to use our LPC underscore ADC underscore ADCR. So this is what we have to configure here, ADCR. LPC underscore ADC. So what is ADC? You know that already. Okay, if you just is correct, no problem. So LPC, okay, ADC, ADCR, channel number 2. Yeah, here you can see channel number 2 I'm selecting, then clock division by 23, burst mode on. Yeah, so this much only the configuration for ADC. This is my first function, ADC configuration. So I hope this is clear. Now we'll go to conversion part, the second function. In the conversion part here, this is the ADC conversion part, and I will be keeping one return type, that is a local temperature. Okay, so now if you want to check the return type, I have to do one small thing. I need to check done bit is set or not. Check done bit is set or not. So in the theory part already I had told you how the ADC works, and after conversion ADC will generate one done bit that is called as end of conversion bit. So that particular point we have to check here. So we have to check whether done bit is set or not. So how to check that? For that we have to use something called polling statement. This I'll explain later, maybe in some other video I'll explain what is a polling statement, but here I'll just directly write the polling statement in order to check the done bit, whether done bit is set or not. So we have ADC ADGDR register, ADGDR, that stands for a global data register, and this I need to AND with our done bit. Here you can see done bit already I have defined with a macro. Just you can use that and then just put it semicolon here. This particular statement is called as polling statement, and this polling is used to monitor the certain conditions. Okay, so certain condition here I'm going to monitor done bit. Okay, so now this is a first point in the ADC conversion. I have to check whether done bit is set or not, and after that I'll be just collecting the data from the data register. Okay, so here the comment, I'll write it like this: extract ADC data, extract ADC data value. Okay, I need to extract ADC data value, and this will be available in a ADDR2. Okay, so there is a register called ADDR2. ADDR2 in the sense ADC and then ADDR2. ADDR2 is a data register for channel number 2, and then I need to go for 12-bit masking and with a bit number 4. Okay, so this particular statement will extract your data. Okay, and then finally you just right shift. So I have to right shift by 4 position to get it as a LSB, and then divide it by some 14. So you can, it's need not to divide. For simple understanding we are just dividing. It is not necessary to divide. Okay, so this much is a ADC conversion program, and then finally we are going to return to the main program. So this much is the second function, ADC conversion, and in the main code here you can see this is the main code. This part is your main code. In the main code we're not doing anything, just we're going clock configuration. If you're using LCD, I'm using LCD configuration, and then ADC I'm just calling the function ADC configuration, and then in the while of one, what you do, I have created one global variable here. Just you can collect your ADC conversion data. That's it. I'm going to collect ADC data here, and if you want you can print it. If you have LCD you can print it, and if you don't have LCD you can just check output in the simulator part, debug simulator. So this much is a program. Two important things we have to write. One is ADC configuration and one is ADC conversion method. So ADC configuration, you just watch the video once again, you will understand. So we have done ADC configuration, this function, and then ADC data collection in this, and after converting the data I'm going to collect it in a one of the global variable, and with a small delay. Okay, I hope program is clear. If you're not clear, you please watch once again, you will understand what is the logic. So now what I will do, I'll just compile and then I'll go for output demonstration in the simulator, debug simulator only. Okay, so there is an error here. Yeah, now the error has gone. So please do remember one important thing, in which channel we are which channel we have configured. So you watch once again the video. I have already explained you. We have configured analog input to P0.25, and to that we are assuming that there is one sensor. If you have LCD option, you can display output on the LCD, but today I do not have LCD, but instead of LCD I'll be showing output only directly on one global variable. Okay, so let us go back to the software here, and I have already run the code. So I'll just go to debug window. This is a debug window. I hope if you're watching my channel, you'll be knowing what is this. This is called debug window, and here you can see this is this part what I am highlighting. So this is called watch window. So here you can add global variables. This watch window will support only for global variables, not for local variables. Okay, so enable watch window, and whatever you're taking variable, in my program I have taken variable called as something called temperature data, something temporary data temp. So I have kept it here already. So I have kept it. And second point here in for the demonstration is I have to open two things. One is go to peripherals and keep open ADC or AD converter. Open this AD converter and keep it aside, and then go to peripherals and open pin connect block. Okay, so these two, this is not necessary, but just I wanted to show you how it is configured, our uh, how our pin configuration got configured. That point I just wanted to show you. I'll put one break pointer here, line number 41. I'll put one break pointer here. Double click. When you double click in a debug window, the break pointer will be created. So this red mark it's showing now, this is called break pointer. Okay, so I have kept on break pointer, and just I'll run for a second here, observe what is going to happen. So now first I will show you in the pin connect block. In the pin connect block, yeah, so observe 0.25. This I just wanted to show you. So 0.25 is configured as analog input to AIN2, analog input to. That means the configuration is perfect, and 0.25 is configured as analog input. Rest of the pins you can see it is showing as GPIO. Correct, right? Okay, so this is clear to all. Now I'll come back to ADC register. So this block what you are seeing, this is your ADC peripheral information. Okay, and here we want to observe. There are two important things we have to observe. One is this one, this part. So I already told we have 8 different channels. You can see here ADDR0, ADDR1, 2, 3, 4, 5, 6. So 8 different registers available, and here also you can see 8 different results they have defined here. Result 0 and up to result 7. Okay, then the whatever we have done the configuration, PDN bit and channel number selection, the channel selection I given as 4. Here you can see that 4 is also available here. Burst mode we have enabled, PDN bit we have enabled, clock division I have given 23, hexadecimal it is 17. Okay, so analog ADC clock is getting 1 megahertz. ADC clock is getting 1 megahertz here. Okay, and then one more important thing with respect to this block is here analog inputs. This down part you can see, this part is your input part. Okay, so we have 8 channels and 8 different inputs you can configure, 8 different inputs you can give here. Analog input 0 to analog input 7, and this is what even I have shown you in the calculation. In the theory part, we're going to use a reference voltage of 3.3. right? So this is the description of your ADC conversion block. So my scope in this demonstration is analog input to 2. Okay, so I will show you 3 different use cases. I will go with a 1 volt, I'll go with a 2 volts, I'll go with a 3 volts, I'll go with a 1, 2, then 2.5, 2.5 volts, and then 3 I'll go, and then I'll go with a 3.3. So I will show you output for 4 different use cases: 1, 2, 2.5, 1 volt, 2 volt, 2.5 volts, then 3 and 3.3. Okay, so these 5 demonstration I'll show you how ADC will convert and how we can check the result. Okay, so now currently I have kept it with a 1 break pointer, and then let us go with the first input, that is analog input 2, and here it is editable. You can easily edit your inputs. You should not go beyond 3.3 volts. You should be there within 3.3. So I'll just give 1 here, and then, so do remember I have given one break pointer here. My microcontroller is stopped in the line number 41. Okay, so now I'll run and let us observe what is going to happen. Now you see here ADDR2, this point you can see here ADDR2. So ADDR2 got some value, and even here you can see we got some value here, 58, right? So this 58 is, there is a difference, right? So why there is a difference? Let us check here. I will show you. So let us keep it in programmer mode, and keep it in hexa mode. So what is our digital data? 4D9, right? So 4D9, and keep it in decimal, divided by 14. Yeah, now you can see. So hexadecimal value is 58, and actual digital data is 04D9. In the code we are dividing by 14, so that is why our manual data, or you can, the variable is getting updated with 58. So that is, this 58 is from here after dividing by 14. Your digital value is divided by 14. That is why your local variable is getting 58. Okay, so this is my first use case. I just wanted to show you. Second use case, so again I will change. Let us go for 1.5 now. I'll go for 1.5 and run it once again. Now you can see the result got something 745. Similar to that, your temperature data also got updated with some value. And then finally I'll go to 2 volts. Now you can see the data. Okay, I need to run it here. Yeah, now you can see data got changed, 09B2. Similar to that, here also it got changed. And then I'll go to 2.5 and then run it. Now you can see ADDR also got changed, and and finally I'll go for 3 and let's run it once again. Now you can see, so it is getting different value, updated value. Here also it got. And finally I'll go for one last use case, that is 3.3. For 3.3 you should get 3 Fs. Now you can see here for 3.3 is the maximum value that ADC can read, and that value is FFF. Okay, when you divide it by 14, that is getting value with 124. Okay, so this is your ADC programming. So if you're not understanding the program, please watch the video once again. You will understand very clearly. I have explained step by step, each line by line code also I have explained, and then I have written, and also I have shown you how to check the output in the simulator, debug simulator. If you have a board, same hex file, you can flash it into controller and you can check the output in the LCD as well. Okay, I hope this video is informative. Please click on like button and subscribe my YouTube channel to know more about embedded system. Let us meet in the next video. Thank you for watching.